when we first see the binomial theorem, it may just seem like a bunch of mathematics and just some type of algebra that very few people would want to engage in. But it turns out that the binomial theorem is used very extensively in probability, in other mathematical fields. So understanding it and using it well is very important. So one of the things that we've noticed with the binomial theorem is that in order to expand the sum of two variables raised to the nth power, that's going to be the sum from j equals 0 to n of n choose j x to the n times y to the, n minus j, y to the j. So when you sum the two powers together, n minus j plus j, it's useful to note that the negative j and the positive j cancel out. And so the sum of the two powers on x and on y has to add up to the number of factors that we have. And of course, this looks in kind of term by term form: n choose 0, x to the n, y to the 0, plus n choose 1, x to the n minus 1, y to the first, plus etc., all the way until we get to the nth term, which is n choose n, x to the, in this case, x to the 0, y to the n. And using this theorem often allows us to take something that looks daunting and complex and reduce it down to simplicity. So there are a series of corollaries, and corollaries are kind of the consequences of a theorem. So the consequences of a theorem, of this one in particular, are widespread. So here we're going to say that if you take all of a bunch of combinations and add them together. So for example, if n was equal to, let's let n equal 3. And so in this case, if what we wanted to do was to calculate the sum of all these combinations, 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3, then that could be a daunting task because each one of these would need to be expanded. So 3 choose 0 is 1, this one is 3, this one is 3, and this one is 1, which is basically the third n equals 3 rows. It's the fourth row of Pascal's triangle, and we can see that these sum to 8. And that's the same answer that we get, arguably, if we took 2 to the third power. Well, 2 times 2 times 2 is exactly 8. So rather than having to add up all of these terms, this right-hand side gives us a quick way to say, if what you want to do is add up a bunch of combinations of choosing n things, and choosing them 0, 1, 2, all the way up to n times, and you want to add these together, the sum is more easily calculated by just taking 2 to the nth power. But how do you prove this? Where does this thing come from? Well, we're going to start with the left-hand side, and via a series of equalities, we're going to show that this equals exactly what's on the left. Now, this is not working with sets, so we don't have to prove subsets of, because these are just numbers. These are not sets of numbers. You can see 8 and 8, those are just two numbers, and therefore two numbers are equal if they're the same. Well, here's one thing I could do here. 2 to the n is really, another way of writing that is 1 plus 1 for that base raised to the n power. Okay, well, by the binomial theorem, what I could say is that if I have some number plus some number to the nth, that's going to be the sum from j equals 0 all the way up to n of this expression here, where our x and our y are both equal to 1. So what I would have is, in this case, n choose 0, so j is 0, 1 to the n minus j, so 1 to the nth, 1 to the 0th, right? So x and y are both 1 in this case. All I'm doing is using 1 for both of those bases. Plus, I would have n choose 1, 1 to the n minus 1 times 1 to the first, plus n choose 2, 1 to the n minus 2 times 1. And I'm going to have a bunch of these terms. I have n of them, so I can't write them all out. I don't know what n is equal to, but the final term will be n choose n, 1 to the 0 times 1 to the n. That's the value of j. So n minus n in this case is 0, and that's our last term in that sequence, or in that series rather. But notice that these are just 1 raised to a power. And if you raise 1 to any power, you just get 1. So what this reduces down to is n choose 0 plus n choose 1. Again, I have 1 to a power times 1 to a power, that's just 1. Plus n choose 2 plus all the way up to n choose n. Well, this is really just the sum from starting at, I'll use k since we're using k, from k equals 0 to k equals n of n. Notice that all of these, the set of all objects that we have in this case, there's n of them, and the only thing that changes is how many we're choosing, and that's going to be the value of k. So this will be the same thing as n choose 0 plus n choose 1 plus n choose 2. And we have proven this corollary because we see that we have a bunch of equal signs, right? All of these equal signs say these things are all the same. And since these things are all the same, we could say that 2 to the n is ultimately equal to the sum of all of these all of these combinations. And this didn't require that much work to prove this. We were just able to do it by utilizing and choosing specific values for x and y in the binomial theorem. I think these are really fun because we can really take off with these and prove other things as well. So let n be a positive integer, then the sum of all of the terms of the form -1 to the k, from k equals 0 to n, of n choose k is equal to 0. Well, what does this mean? Okay, well, let's say that n is equal to, we'll pick 3 again. So by the left-hand side, this means that that would become -1, so the first value of k is 0, times n, which is 3, choose 0. That's our first k value. Our index starts at k equals 0. We're going to add to that because we're summing the next term, which would be -1 to the first, 3 combination 1, or 3 choose 1, plus we'll have -1 squared, 3 combination 2, and our final term would be -1 to the third, 3 choose 3. Okay, now we're claiming that this is going to equal 0 if I add these together. So let's see here. -1 to the 0 is 1. 3, there's only one way to choose 0 objects from 3. -1 to the first is -1. 3 choose 1 is 3. Oh wait, I already know what these are going to be. This is from the fourth row of Pascal's triangle. This is going to be 3. This is -1 squared, which is +1 times 3. And so you can see that the alternating, because we have -1 to a power, every term is going to go positive, negative, positive, negative. And this will be -1. There's only one way you can select 3 items from 3. And so you can see that this term, this term, this term, and this term cancel out, and these 3 things sum to 0. But that worked for n equals 3. How do we know that this always works? So to set this up, what I'm going to do is, again, I'm going to start with the right-hand side and show that that leads to what's on the left. So how could I get 0 by using this binomial theorem, this expansion of x plus y to the n? Well, there's lots of different ways you could do it, but one such way, the simplest that I could think of, is to say that we have -1 plus 1. That's another way of writing 0. And in fact, if I take 0 to the nth power, n is a positive integer, so 0 to the 100th is still 0, 0 to the 1000th is still 0. And what this allows me to do is now I've introduced a use for the binomial theorem. So binomial theorem says we're going to sum from whatever we want the index to be. I think up here we chose j, so j equals 0 up to n of n combination j. Okay, well, wait a minute. So our x is -1, so this will be -1 to the power of n minus j, and times 1 to the power of j. Okay, so how do I begin working with that? Well, let's see. Well, I could start to expand this out, but I see that there's going to be a 1 to the j power here. And if I raise 1 to any power, that's just going to be 1. So since that's 1, I'll have 1 times this quantity here. Well, all of these individual terms will have n choose j, negative 1 to the n minus j times 1. So this is really just the sum from j equals 0 to n of negative 1 to the n minus j power multiplied by n choose j. Well, that doesn't look the same. That seems to be, well, our index here starts at k equals 0, and we have negative 1 to the n minus j, or at least we should have negative 1 to the j of n choose j. So, gosh, sometimes these things require us to shift things around a little bit. So how about I do this? How about instead I choose to write this as negative 1 and write this as positive 1 and make this one over here plus a negative 1. Well, that's not really going to change a whole lot other than which signed value of n, which signed value will receive n minus j and which will receive j. So let me erase this here and see if we can't come up with the exact same answer. For consistency purposes, maybe I should just switch this to k. I mean, j, if we end up with the same thing, but k's are replaced with j's, that's the same answer. But let me go ahead and say this is k equals 0. So this will be n choose k. This will be positive 1 to the n minus k multiplied by negative 1 to the k power. Ah, there it is. All right, so anything, or 1 raised to any power is going to equal 1. That's always going to be a 1 right there. And so because it's going to be a factor of 1, I could omit the factor of 1 and just say that this is the sum from k equals 0 up to n of n combination k. And then I could just, because these are being multiplied together, it doesn't matter what order I multiply them together in, so I'll say negative 1 to the k, which is this factor, this is all multiplication signs, times n combination k. And I'm done. I've proven that because these are all equal to each other, that the first thing in the equalities is the same thing as the last thing in the equality. Now, what I wanted to demonstrate here is that sometimes the way you construct, in this case, the 0, it could happen a number of different ways. So finding out how to represent them is a matter of experimentation. Now, the reason I chose 1 and negative 1 instead of, say, 2 and negative 2 is because I knew that I wanted to get negative 1 to the power of k. So by choosing 2 and negative 2, one of these would be a 2 and the other one would be a negative 2. And 2 raised to a non-zero power, 2 to the third, 2 to the fourth just keeps getting bigger and bigger and bigger. So choosing 1 is a smart choice because 1 raised to any power is just still going to be 1. So all these corollaries start to emerge and all these different properties can become useful at some point. All right, how about this next one here? Here I have 3 to the n, and I want to show that if you sum up 2 to the k times the n combination k, that's the same thing as 3 to the n. Well, again, I just want to get a little bit of intuition. I want to make sure that I'm convinced and that I understand what this is saying. So this is going to be, we're going to start at k equals 0, so 2 to the 0 times 3 choose 0 plus 2 to the first times 3 choose 1 plus 2 squared 3 choose 2 plus 2 to the third 3 choose 3. Now, again, I know from Pascal's triangle that these are going to become 1, 3, 3, and 1. Now, in the final video, we're actually going to make the connection. We're going to show that in fact combinations are related to Pascal's triangle. All right, 2 to the 0. This is going to equal 1. This is going to equal 2 times 3, which is 6. This is 4 times 3, which is 3 choose 1 is 3, 2 times 3. Yes, so 2 squared, that's 4 times 6. Excuse me, 4 times 3 is 12. 8 times 1 is 8. These add up to 27. Now let me check if 3 to the third, would that give me the same answer? Well, 3 to the third is 3 times 3 times 3, which is 27, and I get the same answer, but rather than having to add up all of these, it's much easier to just take 3 to the third power and get that sum in a different way. Okay, so finally, let's go ahead and establish this. So I see that here I'm going to want a 2. So to rewrite 3 in terms of a 2, the one way I could do this is to say 1 plus 2 to the n power. Okay, the reason I chose that instead of 2 plus 1 to the n power is mainly because this x is raised to the n minus something. So I really want 1 to be raised to the n minus something and 2 to be raised to just the something. So by the binomial expansion, this is the sum from, we'll use k equals 0 up to n, of, let's see here, according to the binomial theorem, this will be n choose k times x, which is 1, right over here. It's going to be 1 to the n minus k times the y, which is 2 raised to the k power. Now, once again, here I have 1 raised to a power, which is going to be 1. And so this establishes that the sum from k equals 0 to n of n choose k, but since these are all multiplied together, I'll go ahead and write the 2 to the k first times n combination k. And again, by equality of all of these things, the first is equal to the last. And remember, the first, this is the same thing as saying 3 to the n. So again, a formula that allowed me to do a lot of computations by just one step. Yes, you could sum all of them together, but imagine a computer trying to sum up all of these terms up to n equals 1,000,000. That's going to require a lot of computational power. We've just reduced that computation to a simple exponential function. And these are just some of the corollaries. There are many more that we can explore based upon this. But in the final video, we'll go ahead and make the connection between Pascal's triangle and the binomial theorem. I've been alluding to this idea that for example, up here, or I guess in a previous video, oh, here we did it, 3 factorial 0, or 3 combination 0, 3 combination 1, 3 combination 2, 3 combination 3. I said, hey, these are the numbers from Pascal's triangle, but I didn't tell you why. And in the next video, we're going to make sense of why that is.